Our next presentation is titled Nonlinear Moment Curvature, Response and Ductility of Hybrid Reinforced Concrete Columns. It's a brief introduction of his background, and take it away from there. Thank you.
Thank you. Welcome everyone. My name is Sherif Osman. I'm a PhD candidate, and this work has been done under the supervision of Dr. Shahriar Alam and Dr. Shamim Sheikh. Today I will be presenting the nonlinear moment, curvature, response, and ductility for hybrid reinforced concrete columns. This is my outline for today. And since the room is already filled with experts, so I will not go through the introduction. I will save that time for the next slides. We all know about the harsh winter and the icing issue, which cause corrosion, and the corrosion problem is responsible for the collapse of structures in North America. And rehabilitation of infrastructure costs a lot of billions of dollars, and there is indirect costs associated, especially and unquantifiable when loss of life occurs. GFRP is our choice in terms of corrosion resistance and viable reinforcement option. So as we have seen today, we have GFRP reinforced concrete columns has demonstrated a stable response, and this is characterized by high drift ratios, failure, and energy dissipation. And this confirmed the confinement efficiency of GFRP as well. In the literature, we have seen that the GFRP reinforced concrete columns, researchers tend to increase the spacing and put large volumetric ratio in if they want to comparably have performance compared to reinforced concrete steel columns. So just to compare them together, or just to put things beside each other, if we have a steel reinforced section, usually from a design perspective, it is designed to be under reinforced, where we allow yielding of steel before crushing of concrete. And this usually exhibits a pinching effect in the hysteresis curve because of the inelastic deformation associated with the steel yielding. And this also yields to higher residual deformations compared to a GFRP reinforced concrete columns, where we maybe allow concrete to fail prior to the rupture of FRP. And it should show better hysteresis curve, which is directed to the origin because of the linear elastic properties of the GFRP. We all know about again, it should also lower residual deformations. We know all about the low stiffness and the higher P delta effect and the lower lateral resistance, especially at the first or earlier stages of the loading phase. If we have a hyper GFRP and steel section, and I was lucky to be, or maybe not lucky to come and present after Dr. Sheikh, that the hyper term has been used when the GFRP spirals is provided, while the steel longitudinal reinforcement is carrying or directed towards the capacity of the section. Here I'm talking about another term when it's talking about hyper. If we have the chance to use both of them in the same section to overcome the limitation associated when only GFRP or steel is used, if we were able to push steel away from the surface, we will better provide corrosion resistance, and and of course we're going to benefit from using both materials together. So I am talking about something like that, where we have steel and GFRP together in the section, and when I mean together, we can assume that it is together as a longitudinal reinforcement and as a transverse reinforcement. This layout does not serve the purpose much because both are the same layer, so they have both the same level of exposure. But still, it could be used for other purposes. So maybe something like that, where we have the steel placed at the inner layer, and we have the GFRP placed at the outer layer. But unfortunately, this work has been done on a steel sections, where we have the longitudinal reinforcement made of regular steel, and the spirals made of high strength steel. But it did prove the concept in terms of the deformation capacity and how much it was enhanced by using the idea of having double layers of confinement. Something like that may be closer to what we are suggesting, where we have steel at the inner layer, GFRP at the outer layer, but still this specimens has been done on a smaller scale and only under axial load. So we all know about lack of test data, especially at the seismic loading, under seismic loading. We have seen today and in the literature a lot of research done on GFRP reinforced concrete columns, either concentrically or eccentrically loaded. We have seen few work has done towards the seismic performance of GFRP. I would say there still is a serious lack of published results on a large scale of GFRP RC columns. Maybe Dr. Shamim work that has been recently published is somewhat directed towards this this area. So we all have the bridges, we have the lateral force resisting system. We are concerned about the deterioration happening, which is causing again the corrosion, and when earthquake excitation happens, our infrastructure are extremely damaged. And we need to propose something that it will, first of all, will be provide the stiffness and the strength enough. It should be also reducing the permanent deformation, have some kind or a mechanism of ductility, and last but not least, sustainable solution. And this is my area of research, performance-based design of hyper-reinforced bridge piers reinforcement. So the overall objective of the research is to experimentally document how bridge piers with hyper-reinforced column, FRP and steel would perform under cycling loading. And in order to break it down, in our today's presentation, I will, because of the sake of the time, I will just more focus on that part where we need the analysis tools, and especially the one related to moment curvature. So this is the entire, I just wanted to give you the full image of the research project. Then I will just focus today on that part for the sake of time. For our proposed system, we have the conventional concrete column with the steel rebars and steel longitudinal reinforcement, and we want to change that to a hyper section when we have steel on the outer layer, steel in the inner layer as a longitudinal and a spiral, and GFRP on the outer layer as a longitudinal and as a spiral. Can we do that in one step? Of course, we are changing different factors and many factors at the same time, so we have to have intermediate steps where we can test our hypothesis and check our system. So we start with a material testing program. We take three different types. We all know that GFRP are again dependent on the way they are manufactured and the different coating types that we have. So we pick different material types and we test them. We also attach the digital image correlation system to better see the deformations and the strain happening. We focus on the first part only on under the characteristics under tension, and we did some preliminary results. We reached I would say the high modulus GFRP providers, and we have them all on board. We are now conducting the the first phase when we're gonna finish the material testing program on a different GFR number 3, 4, and 5 under tension and under compression. For example, we have to validate the different data sheets provided with the manufacturer with their quality assurance or quality testing done at the manufacturer, and as well as with our own material testing program. The ASTM 7205 is the standard testing procedure to be followed, and again which is defined the gripping mechanism and everything, and how we wedge it in our MTS loading frame. In terms of compression test, we're gonna do changing the unsupported length ranging from 2 dB to 16 dB, which will first of all cover all ranges covered in the literature, as well as establish the relation between the length and the compression strength of GFRP. And as we have seen today, the compression strength of GFRP has been reported, I would say 40 sometimes to 50% of the capacity of the tensile properties. This is the standard, the procedure that is going to be followed. The standard material testing for steel and concrete has been conducted. Moving to the numerical part, we have our, as I said, our conventional section, and we have our hybrid section. So for hybrid section, the behavior is different because of the nature that FRP doesn't have yield. We could have different approaches defining the ductility. The energy-based approach or the displacement-based approach could be used in terms of defining the ductility. Numerical modeling of the hybrid reinforcement sections and the effect analysis of hybrid reinforcement on the ductility and the strengths will be covered in the next slides. So here are the material models used, I will schematic material models used for concrete, steel, FRP, considering and ignoring the compression strengths of GFRP. For concrete, we use the average effective confinement model for model concrete. Regarding the numerical model used, we used S-CALC, which is part of software of S-Frame, and for the validation process. So we looked in the literature and we found the hypersection for reinforced concrete beams, both reinforced by steel and FRP, as we can see in the sections provided. And this has been also numerically validated in the literature by Kara et al. 2015, and we use S-CALC to validate that as well. And we picked one of the sections for the sake of the time, and you can see here perfect matching with the, I would say, the numerical validation and the experimental research. It was perfectly matching until later stages of testing, and we could, of course, justify that to different factors happened during the test, but for the sake of the time, we'll just proceed to the next step. So we move to our specimens, where we have different specimens. We have a control specimen, we have a hybrid section, and we have I would say, a control specimen where both of layers are steel. So the first and the specimen 0 and specimen 1, specimen 0 and specimen 1, both specimens were reinforced by steel on a single layer or a double layer. Specimen 1 and specimen 2, we are changing the outer layer from steel to FRP. Again, S-frame has been used, and fine model has been, or meshing has been adapted near the reinforcement to precisely allocate the steel rebars and FRP rebars. You can see here the moment-curvature analysis and how did we define the end of elastic phase for FRP and the ultimate value, and we can both from both the ultimate over the end of elastic or inelastic deformations or curvature, we can define the ductility of the section. So we did, again, as I said, this is part of a big research project where we did also fiber element based model for the pushover and non-linear time history analysis. I will just focus now on the moment curvature part. So in the figure here, we can see here the control specimen, and we have a different approach. If we want to design something, maybe we can follow the equivalent energy approach, where we would like to have the energy or the area under the curve equivalent area, or we are just matching the capacity, the maximum capacity of the section. And on the right hand side figure, you can see different hybrid sections with different changing different parameters. So this is also we were going to discuss in the couple next slides. So 2 to the power k factorial analysis were conducted. Table 1 shows here the 4 parameters that we have selected in the analysis at high and low levels. These are mainly the GFRP reinforcement ratio, the steel reinforcement ratio, the outer layer or the external layer over the inner layer diameter, the ratio, and the ultimate strain of GFRP. The values picked here are determined based on the CSA code standards when it comes to the minimum and the maximum spacing constraints, as well as the preliminary analysis findings. So when multiple factors contribute to the behavior of an element, we could run a full or a fractional factorial analysis. So for the sake of the time and because of the number of runs required, we started by a fractional factorial analysis. where we tested, as I said, the different parameters at high and low level, and we checked the interaction. And from there, we were also capturing the maximum moment, the corresponding curvature at that maximum moment, the post-peak maximum capacity. I mean by that, the moment after the maximum, how did it drop? Did it drop significantly, or still there is a capacity or a holding capacity in the section, and the energy dissipated by the section. The analysis revealed that the reinforcement ratio for steel FRP and the ultimate strain of GFRP are the more significant effect factors. These parameters has been taken in a full factorial analysis at 3 different levels. And from, you can see here on the left-hand side, changing the reinforcement ratio, the GFRP reinforcement ratio from 0.64 to 1.15 did increase the section capacity, but still I would say by 40%, but still the post-peak capacity, it did not show much increase, and the energy dissipation by the section is almost the same. However, on the other hand, changing the steel reinforcement ratio from 0.74 to 1.25 almost did surge the post-peak capacity by 70%, and increases the energy dissipation as well by 70%. It did also increase the capacity by, I would say, 25%. So interaction effect revealed that the steel reinforcement ratio is directly proportional to the moment capacity and the energy dissipation of the section. And also the GFRP reinforcement ratio influenced the maximum moment of the section because of the higher, of course, ultimate strength capacity compared to steel. From there, we designed our experiment, and we have our control specimen, and we have the second specimen where we split the total reinforcement ratio over 2 portions, external and internal, but again, both are steel. And we were at the point where you have to decide for the next specimens, adding the GFRP. From a design perspective, should it be a replacement to the steel or an addition to the steel? Both had their applications. A replacement for a steel could be a design choice. An addition to the steel may be a repair choice or a retrofit choice. But from our numerical analysis done, we concluded that the steel percentage between 40 to 66% did show a better seismic performance in terms of moment capacity and energy dissipation. So we excluded this option. So now we are talking about replacing the steel with GFRP. As I have shown you in the couple of previous slides, the different parameters conducted. And this has also been validated from the literature through a double reinforced configuration section, where they highlighted that a reinforcement ratio of 66% did show the best performance, seismic performance. So I will again give you a full image of the test setup and the experimental program. So we are testing. You can consider it as a half-scale specimens with 20 inches in diameter, 508 millimeter, 5 tons of weight of a specimen. So this is our test setup, and under cyclic loading. And we did everything in our laboratories and LAMS lab at UBC, from formwork, steel work, and casting. We just made use of the spirals, like we have to get them ready, and casting, of course, ready mix concrete. All other work has been done by myself and by the help of my colleagues.
I'm sorry to interrupt, but I would appreciate it if you move a little bit faster.
Yeah,
sorry. A little bit behind. Thank you, though. That's all right.
Sorry, never mind. I'm just wrapping up. So this is the test setup. As I told you, we are mainly concerned about the performance-based design guideline or preliminary guideline for this one, where we will identify the minor, moderate, and major and collapse damage states in the later stages. And this is my publications out of this work so far, and this is my references. And I would like to acknowledge S-Frame, NSERC, GFRP suppliers, and steel suppliers as well. Of course, Dr. Alam and Dr. Shamim Sher for their guidance and supervision. Thank you, and you're ready for your questions.